So hi Ted, hi Tony,
Hi.
nice to see you guys. So we've got Andrew coming in as well. Hi Andrew.
Hello.
Do you still want to talk about your hydrogen line stuff tonight?
Yeah, why not?
Why not? Okay, great. I don't know. I think we seem to have a quorum. We can get started. Thank you guys for coming back for meeting two of this. It's wonderful to see you here. I certainly enjoyed the first meeting. I am attempting to record this, as I was just saying to people before you joined, Andrew. I've clicked the record. Oh no. I've clicked the recording button on Teams, but whether it actually is recording or not, I have no idea. But I have got like a backup plan, which is debut. But I did have some complaints last time about the quality of the recording, so we'll see what happens anyway. So, as far as the agenda is concerned tonight, Alex Pettit was meant to be joining us to give a little bit of talk on Hydrogen Line 3D, but unfortunately he's had to opt out last minute for reasons unknown. And Ted has kindly stepped in with a talk of his own, and I've actually had a preview of that talk the other day, and I've got to say it is very good. It is quite advanced, but it is just shows you what can be done with hydrogen line work, and if nothing else, hopefully would excite you to it. We've got Tony here, who kindly offered to give us a little bit of a talk on the theory behind the hydrogen line stuff. I've got to say, I'm personally looking forward to that very much because, as I've said to you before, I don't really understand anything I'm doing. So anybody that attempts to try and explain it to me is worth their weight in gold.
I'm not sure I know as well, but let's have a go.
Oh, well, you're having a go at attempting to do it. That's all that matters. Yeah. And really out there is Andrew here, taking the challenge, saying he's going to come out and tell everybody about what he's hoping to achieve. So I think he's the one that really deserves a clap on the back for taking that risk and going out into worlds unknown and telling everybody else about it. So I would suggest we start with Tony because theory sounds logical to me, and then we could have Andrew. Sorry, then maybe Ted tell us about to stimulate us where we can go, and then Andrew can come in and tell us a little bit about his setup. Now, just as a thought for you all for today, if you wanted to, and for future meetings coming forward. I can't remind myself how many people here are members of SARA. Let's see, Ted's a member of SARA. Who else is a member of SARA here? So we've got three. So every month in the Society of Amateur Radio Astronomy, they have something called a Drake's Lounge, and in Drake's Lounge, everybody gets the chance to say a little something if they want, and it's quite open, and people tend to feel uninhibited in doing that because they realise they're not going to be criticised in any way, and whether you're beginners or whether you're advanced, everyone's welcome. And so I thought maybe in these meetings that opportunity would be there for anybody who wanted to give 5 minutes or even 10 minutes on anything that they're doing or any ideas they've come up with or any questions they'd like to ask. No obligation whatsoever. So if we've got time tonight, we'll do that. We also have a lot of talks. If we don't have time, then we'll do it next time. Okay. So perhaps over to you, Tony, for the just to start us off.
Okay, let me share my screen. Right. Go. Can you see that?
I can. What exactly is the 32 centimetre hydrogen line? I didn't know about that one.
Trying to catch us out in the film.
I think I've caught myself out, yeah.
We're in the wrong bit.
So, where is the 32 centimetre line anyway? Yeah?
Well, there are lines. There are lines that are much lower frequency than 21 centimeters. They're called radio recombination lines. As a matter of fact, I just heard a great seminar from Green Bank. They have what they call the community seminar every other Wednesday, which I highly encourage you people to look up the Green Bank community science meeting. It's fantastic. And this last one that they had this last week was regarding the recombination lines of carbon. And so they can actually look at the temperature of gas clouds that are actually cooler than as a marker for how essentially atomic hydrogen becomes molecular hydrogen. So of course we're familiar with 21 centimeter molecular hydrogen, but and those are fairly high temperatures. But as the temperature cools down and you begin to form molecular hydrogen, you can't detect that, but you can detect carbon that then goes these quantum transitions, and they're down around 200 or 300 megahertz. So anyway, I just thought I'd throw that in.
Yeah, that's very nice. Yeah. Maybe we could do that one for the next meeting.
Need a bigger antenna.
Much bigger.
A very big one, yeah. Yeah. Okay, so I've just put together a couple of slides. I'm always interested in physics. I've been working in IT mostly, but I used to be a physicist about 50 years ago, or no, 40 years ago. I'm not that old yet. So I've done some drawings. The idea here just to be able to sort of talk through it, and it's a lot harder to do this in PowerPoint and Visio and stuff. So, but basically what we're talking about is the hydrogen atom in its ground state. So it's just hydrogen. It's got a proton, it's got an electron, positive charge, negative charge. It can absorb photons, it can emit photons. There could also be interactions between electrons as well. So very basic stuff. And I imagine everybody here is probably quite advanced, or probably more advanced than I am in terms of the knowledge behind this, but let's go on. Okay, so this diagram here is talking about the various energy levels within the hydrogen atom, or at least some of them. There aren't very many. And the reason that you get the photons emitted from hydrogen is, well, I'll take a step back actually. You can get electrons emitted, or photons emitted from hydrogen when there's a drop from, say, a higher energy level here down to a lower energy level here. Can you see my mouse, by the way?
Yes, I can, yeah.
Yeah, great, okay. And then also, you can get absorption of photons, and that can mean that the electron moves to a higher energy level. Now, these are a couple of the specific energy levels over here. So minus 1.5 electron volt, because it's the electron is negatively charged. And then this one here is minus 13.6 electron volts, which is the ground state within hydrogen. And the key thing is all of this is based on quantum theory and quantum physics. So the idea is that the energy that is absorbed or emitted it has a discrete value. This is a discrete amount. So it's a small or a tiny packet of energy. And I've got a little box here. I'll send these slides out if anybody's interested later. But the energy is given by Planck's constant times the frequency. And if you look at this particular example I've got here, the frequency is 2925 terahertz. The wavelength is 102.55 nanometers. And this photon here, this is 12.1 electron volts, and that's actually ultraviolet. That's a UV photon, so that'll make its way from the Milky Way or the center of the Milky Way, and if it manages to get that distance, it'll probably get absorbed by the atmosphere, but you might see it, or it'll hit your skin or something and give you a freckle or whatever. Okay, so energy levels, and so this is the interesting one in regards to 21 centimeter photon. And I say it's a photon, so you can talk about waves and photons and wave particle duality and all that stuff, but I think thinking in terms of photons is a little easier. So it's called a hyperfine transition, and I was wondering what that meant, and I realized that actually means it's a very, very tiny, tiny, tiny transition between energy levels. And for the 21 centimeter photon, the key is that you have the proton, which is a positive charge in the nucleus, and the electron with a negative charge outside. And I've shown this with a sort of an orbit, but we know the orbits are not quite as regular as shown on this diagram. But the key thing is that they both have this spin. And I tried to sort of get to the bottom of what this spin is, and it's probably somebody here might actually know a bit more about it, but apparently it's called the intrinsic angular momentum. So it's an intrinsic angular momentum. It's not actually spinning, but it has a property. It's a quantum mechanical property, which is the spin of the particle. And so the proton has a spin, the electron has a spin, and they're both acting like tiny, tiny magnets. So I've sort of shown this sort of interaction between the electron and the magnetic fields here, with these kind of green lines there. Now, what happens? So the reason you get 21 centimeter photon is that normally the spins are aligned. So the electron and the proton spin in the hydrogen atom are both aligned, and they're both up, they're actually called up, and that's the higher energy state. Now, if as sometimes happens, the electron flips its spin to be down, and that is the technical term, down, you go into, the electron goes into a lower energy state. So you've got this sort of flipping of the spin of the electron from higher to lower, and that also causes the emission of a photon, and that basically is the 21 centimeter photon. Frequency is 1420.4 megahertz, which I think everybody knows, and obviously the lambda wavelength is 21.1 centimeter. And the energy of that photon is very small, and this is why it's called hyperfine, is that it's very tiny difference between the energy levels, and it's 5.9 by 10 to the minus 6 electron volts, or 6, basically 6 thereabouts, 6 electron volts. Physicists and scientists will probably tell me off for saying that. So why does it flip? Why does it actually do that? Why does it go from one energy, the higher, to the lower energy level, in terms of the spin of the atom? So apparently it spontaneously occurs once, or potentially with a frequency of about 1 per 11 billion years. So the chance of a particular hydrogen atom actually flipping from a higher to a lower energy level is 1 for this particular levels. Is 1 in 11 million years, and so it's rare, but there's lots of hydrogen, so you get a lot of these photons will actually make their way from the Milky Way to our detectors. There are other causes, so there can be hydrogen atom collisions, absorption, absorption, emission of photons, and other reasons. The spontaneous emission is interesting. I'll come back to this slide in a second, but the reason for the spontaneous emission, it's relative. It's in respect to quantum field theory. You can see I haven't spoken about this stuff. I usually talked about IT designs and very boring stuff. This is far more interesting. But yeah, it's called empty space is not empty, so there are vacuum fluctuations. And these minuscule disturbances are what cause the spontaneous emission, as far as we know. And that basically causes, so this spontaneous emission caused by these vacuum fluctuations cause the photon to be emitted based on the flipping between the higher and lower energy states. In terms of how old, I've said, well, you've got 11 million years in the making, so that's the probability, 1 in 11 million. And if we assume it's 26,000 light years to the center of the Milky Way, then if we wait for 11 million and 26,000 years, we may see one of them. And So that was all I really wanted to sort of cover. I can try and answer questions. It'll probably be another session where I'll say I'll get back to you on that. But I did also dig out the original paper from 1951, so I'll send that, where the 21 centimeter line was discussed, and I can send that out with the presentation. All right, Andrew, I'll hand back to you, and if there's any questions, I'll be happy to try and answer them.
Gosh, you said you wanted just to give a couple of slides. I don't know about everybody else, but my brain's aching like mad after that. But it sounded like it was really important and really good.
I can happily go through it again. Yeah.
You need to for my sake, but I'm sure everybody else understood it. So. Another day, I'll get you to book separately with me, and then you can use words of less than one syllable.
Sure.
This is noddy, and this is big ears, and big ears goes up to noddy, and that's about right
I
to
thought
me.
that's what I was saying. Yeah.
It sounded really good, actually. Has anybody got any questions that they would like to ask?
I've got a very basic question. When the photon is emitted, is that a single particle going off in a particular direction, or is it a wave going off in all directions?
Well, the fudgy answer is it's both. But for an individual photon, it's the one photon, so it's a single photon. But what you get is, if you get many of these, you'll end up with a wave.
Yeah. So if I detect a particular photon resulting from an energy flip,
Yes.
Ted, based a couple of thousand miles away, isn't going to detect that same photon, is he?
No. I mean, I would say no. He will be detecting other photons.
Yeah.
And again, that's my interpretation of what I've gone through. And again, I'm learning this. So treat it with caution. Yeah.
And that magnifies the improbability of it being of the emission from a particular atom being detected.
It does actually. Yeah, I hadn't thought of that. So I think we all get our own personal photons. Yeah. A message from the universe.
Yeah, it's a singular event. There's a entry-level text here that might help. I'll hold that up to the camera.
Yes. Do you have to have a dog for it?
I found it very useful. He's not that. Yeah, he's not that bright. He's still struggling with the relativity version of this book. But, yeah. Puts it in terms of squirrels and the probability of a squirrel being in a particular place.
Yes, that's a good one. Actually, I've got some squirrels out here out the window. I can't show you. Yeah.
I guess, John, the real question is, if the squirrel is behind a hedge, is the squirrel really there, or isn't it there if the dog can't see it?
Indeed, this is what we're talking about, in effect. It is the Heisenberg bit coming in, that you do see your own personal photon. Because once you've detected it, no one else can detect it because you've absorbed it.
Yes.
The act of taking the measurement changes the outcome.
Yeah. And to think of it, I mean, those photons could have kept traveling forever.
So you're denying somebody else the chance of receiving the photon.
It's indeed.
Yeah. So Tony, I don't really expect you to know the answer to this question. So just say you don't know.
I'm glad you said that, Andrew.
Yeah, but how does changing the flip status of a photon actually lead to it losing energy?
It's so that's quantum. So the fudgy answer is this quantum theory. So the electron, when the electron.
Sorry, can you forgive me? Apologies, the door's just rung. I'm just going to have to go and answer it. Excuse me.
Okay, all right. Yeah, I'll hang on. So I've got a little book here on gravitation I'm going to read, but it's got about 1,000 pages in it. It might take me a while before I'm able to give any kind of presentation on it.
That'll be heavy going then.
Yes,
It's very heavy going.
Very dull.
Literally, yes. That's very good. Yeah.
Very,
I thought it was a really bad joke as well, but I'm not sure.
No, maybe not.
Yeah.
Maybe not.
Andrew, yeah. So the whole sort of idea of energy levels. So So within the atom, the energy levels are discrete, and an electron can be tickled to sort of move from one energy level to the other. So if it moves down between energy levels, or it'll actually emit a photon of a particular frequency or a particular energy. So that's exactly what's happening. So the electron in the atom has actually gone from a higher to a lower state, and in doing that, a discrete photon with a discrete amount of energy, it basically heads off into space towards the Earth for our purposes.
Okay.
So would not be the same effect if rather than the electron changing its up or down spin, the proton changes its up or down spin?
That is a good question. I do not know. I do not know. I'd have to sort of try and dig into that and find out.
Well, isn't it actually not necessarily that the electron loses energy flipping from one state to the other, but that the relationship between the two spins have a particular energy level?
Yes. Exactly.
So when you flip the orientation, it's not the electron that loses the energy.
Yes.
It's the gestalt, the two spin
correct.
states.
Yes. Yeah. No, Adrian. Yeah, you're absolutely correct there. Yes. Yeah, that's a better explanation than
relative.
mine.
I think is the answer.
Yeah, it's still relative. Yeah.
You know, it's interesting that so even rarer than the protium atom, the hydrogen proton electron, you also have an equivalent emission between deuterium atoms. There's also the same equivalent spin flip emission of deuterium atoms, but it's a much lower frequency. I believe it's something like around 700 megahertz or something like that.
Okay.
And of course, deuterium being even more rare than protium, then of course that signal is even much weaker. So that's even rarer to detect, but it is detectable.
Yeah.
So, but just as a novelty there, that is not only the hydrogen atom, but its analog, the isotope deuterium, that also emits the same.
It is interesting. And I think the more you sort of dig into things like this, the more interesting it gets, and the more possibilities there are, such as detecting the emission from deuterium.
So it's interesting that the energy level there is different, just due to the presence of the neutron.
Yes.
So it's an even lower energy level than that proton electron spin coupling there.
Yeah.
Or uncoupling, as it were.
Yes. Yeah, fascinating.
Right. I looked something up which I thought might interest you, just to cheer you up a little bit. Where are we? I've got it here. Right. Radio recombination lines, the transitions of ionized hydrogen. We have, just to show you we're right, Adrian, H182 alpha is at 997.3, from 034 megahertz, 997.034 megahertz, which is very close to the 30 centimeters. So there you are, Tony. You weren't too far off.
I wasn't too far away.
It was just a wild guess.
Just luckily it wasn't
in this case,
third centimeter.
In this case, the one I was referring to, they're actually using carbon as a sort of a marker for these clouds, because of carbon in the form of carbon monoxide and so forth, which is also can emit, carbon monoxide can emit microwave signals. And so they're looking at actually as an analog for determining the temperature of these clouds. And so by looking at these radio recombination lines, that they can more or less ascertain how the process of going from the atomic to the molecular hydrogen. So that was the whole. And these are fantastic seminars. If you're interested in radio astronomy, I strongly suggest you look at the Greenbank Community Science Seminar. It's just fantastic. It's like every other Wednesday and it's only for 30 minutes. It's a short one, so you just if you blink, you miss it.
Tea time. Yeah.
Yeah, but they're great. I have attended these things for years now, and you get some really fascinating talks. Deep. I mean, they're over my head, so I can totally appreciate Andrew's comment, but I have learned so much. I mean, I'm a molecular biologist, so I have no basic hardcore classical training in astronomy, but I have learned so much from listening to these seminars, and I've always loved seminars. Even from graduate school, I just adore seminars. The less I understand them, the more I enjoy them. because I know I'm going to learn so much more.
Yeah.
So much more.
Yeah.
And 3 years down the line, I go, that's what that was all about. And that moment is fantastic. It's just adrenaline flowing through my body. But anyway, I just thought I'd throw that in.
Adrian, can you give us more of a reference to how to get to that?
Yeah, just look on the internet. Look up the Green Bank Radio Astronomy, Green Bank Radio Telescope site, and then look for the Science Community. I believe it's called the Science Community Seminar. And as I said, it's on Wednesdays and every other. There it is. Thank you, Ted. You seem to have your finger on all the links. I mean, every time we need a link, Ted comes through. Thank you so much. But they're fantastic. I just get a thrill out of enjoying the radio astronomy talks, and they're really great. Everything from SETI to the really hardcore radio astronomy presentations are just fantastic. They're really good. I'm sorry, I can't.
I'm just having a look.
Advertise it much more than that.
Yeah, sorry, just to say, I'm looking online at the moment, so anybody looking at the recording will see that I've got it showing here with the link, and I pulled up the web page, and it looks like all the past talks are actually recorded,
They're
so
online,
you can
yes.
go and look
That's
at them.
right.
Yeah.
Yep.
Oh, that's good.
Yep. Yeah, they're just go through those, and you'll just absorb so much radio astronomy, you'll almost be a professional.
Look forward to that then.
So, well, that was absolutely fantastic. Thank you very much, Tony. That was
Cheers.
brilliant
Cheers.
talk,
Yeah,
and a highly professional level of question answering, which is far better than anything I can
very
do.
good. Yeah.
So,
Yes.
for another very professional speaker, let's go over to Ted, who's always worth listening to. How are you today, Ted? And thanks very much for offering to step in last minute.
No problem. We were talking about that cool book for all you dog lovers. Let's see, where's the chat? And so here's the link for that one too. That's all I'm working on. Okay, how to teach your dog. That looks interesting. There are a couple other ones. Having breakfast with Einstein too. It looks like another good one. Okay, let's see. I'm supposed to be on, huh? Let's see. Chat. No, not chat. Pardon me. Share is the word I'm looking for. Share, and I got to bring up pretty pictures. I got a lot of windows. This one I'm thinking. Okay, I'm hoping you're seeing blue.
Yeah,
Yes.
Ezra, RFI data filtering.
Very good. We hope we can change pictures. This is a little quick talk. I'm going to go real fast. You can look at it in the video for the details and stuff, or figure it out later. This talk is supposed to give you hope. This is where our radio astronomy hits reality. Things don't always go quite well, but how can we remove that ugly stuff? Radio frequency interference, and how can we filter out that later on? We collect all this data, and sometimes it doesn't quite go right. Let's say we collect a whole bunch of data, and this is a common graph in the easy radio astronomy, the ESRA stuff, where we have a whole bunch of sample numbers across the bottom. That kind of represents time going forward to the right, and then frequency up and down, because each sample is 256 commonly. You can change that. Commonly different frequency channels, or frequency bins, I'm calling them. So 256 values vertically for each one of these lines going straight up. We can see that over here on the color bar, that yellow must mean a bright power for that particular frequency bin. Okay, that's good. And what we have here is a created example of some neighbor that is turning on his garage light, which gives out all kinds of horrible frequencies and is disrupting your data. Look at all those big, ugly yellow things on there. Where can I see the tiny little signals from space? If we look at this, collect all those samples and add them up and look at the average, the maximums, wow, this is frequency now increasing to the right and power going up. And sure enough, we see the frequency response There's 1, 2, 3 big spikes of data from that evil neighbor. In fact, the left one is a little bit higher than all the others. It'd be a lot better if we could get rid of those. So sure enough, Ezra spits out tremendous amount of information to the screen. I ignore tremendous amounts of it. But ever so often it says something good. When it plotted this graph, it looked at the strongest values for each one of those frequencies and told you about the 5 highest ones. If we took that highest one and called it 100%, then over here on the right, we can see the next one was 97%, a little bit less, but not much. Then 94, and then finally the fourth one goes down to 45% and probably levels out. That's the data we really want. Let's get rid of these top 3 things. In fact, the program even suggests down here, use this big long keyword on your next command and hide frequency bin number 56, this troublesome one. And you might want to even remove the other ones. So you make a command where you run Python, you run the program called EasyCon, which is short for condensing the data. That's the real analysis work. You put in your data file, whatever it is, wherever it is, and then you use these fancy words, EasyCon, something about the raw data, something about a frequency bin and hiding it. And which one? Well, 56. And the same thing for 106 and 206. And I think it kind of matters that you put them in order. Otherwise, the program doesn't quite understand your instructions quite so well. The command isn't that tough. And you get a better frequency response. At least the 3 spikes are gone. There might be another spike you have to attend right here in the middle, usually a mathematical artifact from the SDR computations. And it looks like there's a little bit of bump for galactic hydrogen over here, so that's encouraging. All right, so removing rather continuous frequencies that are troublesome. That's what that was about. But what happens if they happen intermittently, like a lightning strike, or some other spark, or a plane flying over? I took a lot of data one time. This is from June 6 all the way up to May the next year, so about 11 months of data. And down here it says that there are 1.5 million samples. Oh my gosh, it takes forever to calculate all that stuff, to run EasyCon on all that data. Although I do it day by day by day by day calculations, and then combine them later. That's the way that Ezra was designed. Each week, actually, I went out there and changed the elevation of the antenna to point higher and higher in the sky. That's so I could look at different declinations on the radio sky and collect all that data with lots and lots of drift scans. Okay, that's nice. If we took the average of all those samples across the 1.5 million samples, shown increasing across the bottom here, wow, there's something really sticks out. That doesn't look good. That's not going to help. And indeed, if you plot all this on the radio sky, there's that bright signal with the yellows and reds shown in the color bar down there. And the rest of the plot, gets left with the purple. There's not much detail available to show. Let's improve that. I said for each one of these itty-bitty dots on the screen, it actually was the average here of 256 values. What about if we looked for the maximum of those 256 values? It gets even worse. So someplace there was a real maximum signal, and you can't even see any detail later on for the other samples. If we plot those maximums over time, yeah, it's even worse than before. In fact, there are a couple other kind of sharp spikes, whereas the rest of the data is down here in this flat line. We want to see the detail of that flat line at the bottom. Well, we've identified this sample. Okay, what happens if we just remove it. We ignore it. We don't use it. We pluck it, just like a bad something in the way, some bad thing in the grass. You pluck it out. If I pluck out the first one, oh, okay. If there's a concept of organizing all this data, if we organize all these green dot values in increasing order, it's a whole lot like lining up your high school basketball team by height. Some kids happen to be shorter, and then there's this other guy here at the end that's bigger than all the others. That's what happens with our data here. We got, sure enough, a little bit of data here, a lot of them about the same, and then there's this huge thing like some 26-foot high school kid. So that's obviously an error. Let's remove that sample. We can identify what that sample is. Let's remove it. Okay, I removed one sample, the worst one, but apparently it's not the only one. So then I removed some more. Then I started removing them in groups of hundreds, and eventually I got up to 2485 worst samples. And it looks better. I'm seeing detail now in that flat line from the before picture. If I remove just one more, the big maximum over here, then it looks pretty good. I'll deal with that. That's much improved data. If I simply ignore those 2, 4, 8, 6 data samples, what is this value of the very top leftover sample? It turns out the program spits out all this information, I say, and one of them is, for that plot 190, it turns out it will tell you what that maximum value is. So instead of doing it by quantity, now let's filter by value. We're going to run Python, we're going to run EasyPlot, one of the analysis programs, and this big long keyword having to do with the maximum values, plucking those maximum values, and here they are values. It's a list, so I get an L on the end. Remove all the values below 0. Well, up here it says there really aren't any, so that's fine. And remove all the values above this magic number that we found. And then plot, just easy plot, all the plots from 190 to 190, just to speed things up. I don't need the other plots. Well, it comes up with kind of the same plot when we look at the average. That's good. That great big spike we saw in the beginning green plot is gone. Now when we plot it on the sky, wow, that's looking pretty good. Great. So what we need to do is go back and run that through all the EasyCon to create the file for this. And now we start to see some more detail around here, a whole lot better than one great big spike of data down on the bottom. So let me review just a little bit what we did. I said we run EasyCon, that analysis program, on every day's worth of data. This was the 170th day of 2021. And then the next day, and then the next day. I ran each one of those commands, and just to speed it up, I only did one plot. There's a way to automate this process. You don't have to type them all in with a batch file, so I did that for 363 files up here. And then I analyzed it, and we saw problems with RFI. Okay. Problems with RFI, particularly on the 190 plot. I took away the worst sample, the next sample, no, the next 100 samples, and I finally got up to 2486 fairly quickly. This program runs nice and quick compared to the EasyCon program. We got a fancy value, the maximum value, and then we used it with a fancy different keyword that talked about value instead of quantity up here. And got a very nice looking plot again. And so now we have this value that we can use on the slow EasyCon program to filter out its data. EasyCon, this big long word, talk about max, pluck, and value in a list. All the values below 0 we remove. I don't think there will be any. And all the values above this number that we found. And then suddenly the data looks a whole lot better, as we saw. So this is a sign of hope that when reality strikes and you have frequencies that are consistent, well, there's ways to remove those. And if there are intermittent, transient, powerful signals that break certain data samples, there are ways that Ezra can help you find those data samples and pluck them out and make it a little bit easier. So I'm trying to provide you a sign of hope that Ezra can help. Wow. After all that, any questions?
Thank you very much, Ted. That was marvellous.
That's very good.
Fantastic.
Who's not been bowled over too much and got some questions?
So Ted, on those sort of cryptic commands, other than being a Python guru, how would you even know what those commands should be? Those strings.
That's because part of the Ezra files, you get about 32 megabytes of stuff, and a bunch of that is PDFs where it walks you through things.
Okay. All right.
There's hope there too. Take a look at, there's an overview, and then there's what's really helpful after all that installation files are demonstration. So it'll walk you through this step by step, and you can do it on yours and see if you follow along.
Okay.
Thanks.
Thank you. Fantastic. Thank you. Yeah.
Yeah. I mean, I think this is pretty advanced stuff, Adrian. It is amazing what it can do,
Yeah.
but I think Ted's being a little generous to say you could just look at it and then simply walk it through. It is. But what really stands out is he himself is such a tremendous support for anybody that wants it, and he'll spend hours with you, helping you to know what to do. And part of the idea of this group, of course, is to develop a group of people who know the different skills, not just with this, but with other pieces of software as well, too, so we can help each other to do these things.
This talk is really just a sign of hope that there might be a way to do this.
Exactly. So you know it can be done, and it's worth pursuing it. Yeah. And it means any data you've got that may not be showing you what you want it to show doesn't necessarily mean you need to bin it all, but there might be ways of turning it into something spectacular.
So in the documentation, does it kind of go through certain levels where you can progressively get to a finer and finer granularity of these various commands and fine tuning of the data?
Exactly so. Ezra is kind of a teaching tool, and it slowly walks you through a lot of this stuff. There's always a need for more documentation. I'll go for that. But Ezra has lots of knobs and switches, but they all have defaults into the simple position. And so you can start there, and then you can do fancier and fancier stuff as you comprehend what it was you just did. And that demo PDF helps you walk through some of that.
Great, yeah. It's fantastic, yeah.
Yeah, I think that's the most amazing thing, that it is. It's got all the defaults there, which means you get 250 plots you don't understand.
Right, I agree.
So I've got a question, Ted. When you first run this program and you do your first sweep of the sky or track along under the sky or whatever you're doing, will it save all the data that you will ever need? Because one of the things I've found with some other pieces of software is unless you get the settings right, you're going to end up with nice big data files that don't have what you need in them.
Well, I think that the normal process is there's several levels about all this. You collect the data, you go, and while you're collecting, ooh, wow, look, it's kind of bouncing around. Oh, it's doing things. Look, there may be a bump over here, and there's excitement just in that. Later on, it's writing numbers into a data file on your computer, and then later on you can analyze that, and you start to learn other things. Wow, ooh, there's a little bump. There's some consistency to all these different bumps. They might reveal that the galaxy is in this place. So that's kind of exciting. That it happens twice a day with a drift scan, yeah, okay, that makes some sense. And there was another point in there too. But when you collect the data, it collects all the data, and whether you make sense or use it or not. Then there's the other issue. You thought it was pointing south, and it could be that the galaxy will tell you, no, your antenna's off by 2 degrees. And so, you know, you learn along the way, you find out maybe that's not quite set right, or my clock wasn't perfectly set, and when you try to plot the galaxy up on the sky, it will be in the wrong place. Well, maybe you have to go back and check some of these things. This is a learning lesson every time. That's good. At least that's what I experienced. Every day's a school day.
On one of those computations, Ted, you showed that it took 2 hours to run.
Yeah.
Does your files can they utilize things like, I don't know, the GPU in your computer to maybe speed that up, or is that just maybe already maxing out whatever the computational power of your computer is
I think you're seeing that I'm having a pretty extreme case. This was 11 months of data, 24 hours a day, forever. You know, 1.5 million samples, every one of them with 256 values. No wonder, you know, the poor computer. So I try to do it in small little chunks of 1 day at a time. 1 day might be like 20 megabytes worth of data or something like that. So it's not remarkable. And then you can glue them together later, so you're not overwhelming your computer's memory issues. But the calculations in the beginning are complicated. You have to think about where you are on the Earth, what time it is, what part of the sky you're looking at, what is the velocity correction that has to happen. There's a lot of deep math going on in that first analysis with EasyCon. So the next question, I guess, would be what's the weapon of choice regards computers and operating systems? Are you running under Windows or are you Linux based?
This is open source code. I run it on Windows. I run it on Linux without any problem. Other folks have put it on a Macintosh, I'm told. I don't have one. Other folks have put it on Raspberry Pi, and it's working as well. So this is more a Python question. I'm largely running on Python unless you're collecting data. When you're collecting data, now you're talking to the hardware, SDR, and you got to get into the details. Well, I give installation files for both Linux and Windows.
Cool. Yeah, that's it.
There we go.
Pi, receiver, 60 dB preamp, bandpass filter, and antenna.
So my theory is that EasyCal for collect could run on that Pi and write the files somewhere. And then you could study them more at your leisure later on with other programs.
Cool.
And is the data collection sort of agnostic? I mean, can you use like an RSP SDR rather than the...
Oh, yeah. We need to get into picky stuff here. My program currently only supports the cheap SDRs, RTL SDR. And there's a certain chipset there that it recognizes. I think it recognizes the next level up, like for NOAALEC, which has a slightly different chipset in it. This is all a function of the library I use to communicate to it, and I'd like to improve that with SOAPy drivers, which would support all kinds of hardware, and I haven't quite gotten there.
Wow, that would be great, yeah.
If you want help, come on, talk to me. I think we're really close. I have a guy that did it.
for this program, why don't I take his stuff and glue it into mine? And I just haven't been, I've been busy with many projects.
Sure. Yeah.
So Ted, I've written quite a lot of drivers, Linux drivers for the RSP DX and that family. I think John was just waving one at the.
Yeah. They're not very photogenic. It's just a black box.
Yeah.
With a USB connector and a SMA connector.
They're 14-bit converters, so they do everything as 16-bit data.
Do I know those? Do I know those as SDR Play?
Yeah.
Yes. Okay.
Yeah.
Yeah.
Yeah, and that's one I'd like to support too. And I think with SOAPy drivers we could. I don't think my software supports that now.
And they can go up to I think 2 gigahertz over the New Electric.
You're saying a bigger bandwidth? Yes.
The frequency upper limit is up to 2 gigahertz of the actual SDR. It's not limited down to, what is it, 1700 or something on.
Sure. I'm not sure that helps us with hydrogen itself, but okay.
It's
no, not necessarily for hydrogen. No, but maybe your software can be useful for other things. I don't know, like one of the possibilities would be for Maser type observations, perhaps.
Well, certainly I can collect power data, but the timing of things like pulsars and masars, I can't go fast enough in Python.
I see. Wow, that has to be.
A lot of Ezra is discovery and learning about coordinate systems and all that other kind of stuff, and power when presented across the galactic, the radio sky. Let's plot the galaxy.
So the real score for the over the RTLs is the 14-bit ADCs. They're a lower noise floor inherently, and they're higher resolution data. But you can have about a 2 megahertz bandwidth, 2 mega samples bandwidth from them. But so what format are you storing data in that you're then processing? Do you have a guide to that somewhere I could have a read of?
Yeah, do take a look at that website. I got 8 videos that go through all the gnarly details of Ezra. The first one talks about the data format pretty quickly. So that's what I suggest. I suppose it's in the PDFs too. And the data has a couple of things on the front. It says, so what's the name of your observatory? I call mine Little Thompson Observatory. Andrew calls his LRO. So that's nice. Where is it on Earth? Okay, you're about to give me a bunch of data. What are the frequency ranges? And then maybe where are we pointing at the sky for the first sample? You can change that later on in the data file. And then you get a timestamp and then a whole bunch of numbers representing powers of those little frequency bins. What's the color? What's the value of that little blue or red dot? And maybe a little flag at the end telling you what kind of data this is. Is it horizontally polarized, vertically circular? Is it a reference sample to be helping your calculations later? That kind of stuff. It's all in text so that it's fully visible and you can play with it in all kinds of ways. Very simple, minimal.
So any host FFT you need?
The FFT is provided by part of Python, let me say.
So, yeah, so in your actual data you said you had frequency bins. So does that mean that I need to take the data from the radio and do the FFTs on it before I present it to EZRA?
The collecting softwares, just for about everything we use, will take a time domain bunch of data and do it again and again and again. From that, they build up an FFT, and they use FFTs use that frequency spectrum from then on. So we hardly ever do anything in time domain. That's pulsar stuff, not Ezra stuff.
Yeah, no, so I'm looking at if I write a driver to take time domain straight from the SDR, what do I need to do it to make it useful to Ezra?
Ezra cares about power, not so much timing. It just doesn't know how to handle that. So hydrogen out there in space has no timing, so it's just not designed to care.
No, okay, maybe you misunderstand me. So the raw data I get from an SDR is time domain samples. It's 2 megahertz of
Correct.
IQ data.
And the default is you take 31,000 of those and sum them up and add them up and turn them into a one frequency spectrum and write that out as one sample.
Right, okay.
That is a frequency spectrum. Take a look at the videos. I think it'll be much.
I'll take a look at the video because it should be fairly easy for me to do that. I've done it a few times for various other projects, so yeah, that's quite convenient.
Or talk to me because we could do this SDR play. It might be an afternoon's bunch of work. It's just on the list.
Okay, well, maybe I've presumably got your email somewhere. Maybe I'll drop you a line and we can collaborate a bit, because that would be quite useful to do, I think.
Very good. You look up my name, Ted Klein, and Ezra, and there I am. My email's at the bottom.
Excellent.
Please throw in Adult Pluto and Hax RFs in there also.
Yeah, I could probably do it for the Pluto.
Well, once we get the SOAPy, I think a whole lot of them show up.
Yes.
There are a lot of SOAPy drivers already available at the next level.
Yeah. Great.
Thank you, folks.
Wow.
Okay, well, thank you very much, Ted. That was absolutely brilliant. I think we've been really lucky today. 2 fantastic talks. So, moving on to you, Andy. Andrew, do you want to tell us a little bit about what you're hoping to do, and see, perhaps if there's any questions you'd like to ask anybody or suggestions you'd like to make for other people?
Yeah, certainly. I started my hydrogen line observing project in 2017, and at 5 p.m. today, I captured my first bit of data. So it's taken me about 8 years to get it working, and that's pretty rapid progress compared to most of my projects. The antenna is based on a design by Peter East. Some of you may know Peter. He's a retired consultant on microwave systems and electronic warfare from Red Hill in Surrey. And some of you may know him through his presentation to SARA on small aperture detection of pulsars. Back in 2013, Peter published a design for a low-cost hydrogen line radio telescope, and that's the one that I've had a go at building. His original paper was published in the SARA magazine and in the now defunct BAA Radio Astronomy Group quarterly newsletter. And that paper can be accessed through a link that I will try and post to the chat. Just let me copy that. And how does this work? Chat, type a message and post. Does that come up?
Yep.
Great. Peter subsequently published 2 further papers. The first of these covers upgrades to the receiver and to the aerial, in which he describes a 4-element quad element Yagi, the basic designs for a single element Yagi. And the second paper covers further improvements to the receiver designed to minimize the effects of gain variations. I'm not sure whether those 2 papers are available on the internet, but if anyone's interested, I've got copies which I can circulate. So I made the aerial 8 years ago using Peter's design, And I'll try and put a picture of this up, which will involve me sharing my screen.
While you're trying to find that, Andrew, I'll just say hello here to Jeff that's just joined us.
Oh, hi.
I don't know whether you've made a bit of error with British summertime, Jeff, but we're now UTC +1.
Okay, can people see my screen?
Not at the moment.
Okay, what have I done? What do I need to do to...
There's a share button somewhere.
Yeah, I've done that.
It's at the top. Yeah, so you click share and then you...
Slide window, entire screen, allow. Has that worked?
Yeah, done.
Good.
That's what I do as well. I just go for the entire screen. It makes life easier.
Right. Well, that's a picture of the schematic from Peter's original paper that describes the elements in his system. My systems are different. I've got the 22-element Yagi, and then I've got the Sawbird H1 LNA that's been discussed. I haven't bothered with the interdigital filter yet, and at the other end of the system, I've got the Nuelec bias T going into the PC through a USB port.
I can just
so that's what it looks like at the moment on my extremely flimsy tripod. And that is the bottom end of it. So you can see it's a series of brazing rods glued between a couple of strips of 1.5 meter long hardwood, with a bit of coax coming out of the bottom going into an SMA connector. So the element's 22, the aerial's 22 element Yagi with 22 1.6 millimeter diameter brazing rod elements sandwiched between the hardwood. The length and spacing of the rods came out of Paul McMahon's Yagi CAD software, and I will post a link to that in a moment. Does that come up? Yeah, I think that should be visible.
Yeah, that's it.
Okay. The design impedance is supposed to come out close to 50 ohms, although I haven't measured that. And the design beam width is 26 degrees with 18 decibel gain. Again, I haven't thought to measure or verify that. To put the beam width into context, the beam width of a 1 meter diameter dish at 1420 megahertz is about 15 degrees, if I've got that right. So the Yagi's got significantly less resolution than that at 26 degrees. If I've done the sums correctly, the Yagi's beam width is about what you'd expect to get from a 60 centimeter diameter dish aerial. Anyway, having made the aerial, it gathered dust for 8 years until last month's Zoom session, which enthused me and inspired me to take it forward. And the first thing to do was to make a mount for it, which is that. I cut off a bit of 40 millimeter diameter Delrin rod and milled a slotted saddle in one end to take the aerial.
Forgive me, Andrew. If you're thinking that we can see your screen, we can't at the moment.
Oh, okay.
We've lost it.
Let me see what I can do, because...
So I think you'll need to share again.
Yeah. Just a moment. Share. Right. Yeah, so that's the saddle. Is that visible?
Yep.
Okay, so I milled out a saddle in one end and tapped out a 1/4 inch 20 thread in the other end so I could mount it on the camera tripod, which is that pretty flimsy, but it'll do just for a start. The electronics follow the system that we discussed last month with the Sawbird LNA. For the cabling, I used 5 meters of LMR 200 cable with SMA male connectors at each end, one end going into the LNA and the other going into the Smart T. Then I had some fun following Ted's excellent Windows installation instructions, which I commend to everyone. They're extremely detailed and take you through it step by step, and you really can't go wrong. Except that I did go wrong because I had a bit of a failure of nerve when it came to reinstalling the drivers on the LNA. No, is it on the LNA or the Smart T? Well, whichever of them it is, I wasn't quite sure how to do that. So I had a very helpful Zoom session with Ted and Andy, and they took me through it. And today I connected everything up and got some data out of the system, which, can you see that? Is that visible?
Yes, yeah, we can see your
very,
screen.
very good.
Yeah, I mean, it was pointed more or less at the sun, and I just left it running for an hour or so, and I'm not sure how much. Yeah, it's about an hour's worth of data there, and by itself, it doesn't really tell you anything, but it seems to prove that the aerial is picking something up, and that Ted's software is logging that and displaying it in a very helpful manner. So my next task is to try a drift scan of the sun tomorrow, and see how that turns out.
Wonderful, wonderful. Well done.
Yeah, what radio are you using there, Andrew? Which radio are you using, Andrew?
Sorry, which?
Radio. SDR.
Well, it's just the aerial, the Newelec LNA, and the Smart T going into the PC.
Oh, okay.
So, Newelec Smart T SDR.
Oh, okay. Okay.
Yeah.
Are you going to
down
bring...
on the very bottom graph in red, we could see that it started out really hot and then cooled off abruptly, and that's simply the SDR warming up.
Okay.
As it gets hotter, the electronics don't work as well, the gain goes down, and so our signal goes down. This is understandable. And so there's even a button on the top right to say, okay, it's warmed up enough, let's start a new file instead of waiting for the next day to start a new file. All these buttons, I must say.
Oh, Andrew, can you show your picture again so we can see what Ted's talking about?
Sure.
Otherwise, it's just kind of bouncing around with a bunch of noise.
Just a moment.
And this is common.
Another important question for you. The photograph on the drive with the tripod,
Yeah.
that wouldn't happen to be the tail end of a Daimler SP250 showing
Oh,
the
well
corner of the
spotted.
picture.
Yeah, well spotted. It is.
Sorry, can't help myself.
There's you're very impressive.
That's not a bad spot really for me.
No, it's not. It's not. Bonus point for the Fiat Panda.
I wouldn't have spotted that one, but I'll just offer that to the camera.
Oh, very good, very good.
That shows.
Yeah, that's the drop that Ted was mentioning as it warms up.
So which bit's that?
It's in the bottom. Can you see my cursor?
Yeah.
Yeah, it's that's the drop there. It doesn't appear on the last hour because it's dropped off the end. It would be here. and it doesn't appear in this screen either. So it only appears in the bottom one, which is a 24-hour display.
I've found that it kind of takes about 20 minutes for the SDRs to warm up and stabilize.
Okay.
So that's, and then up in the top right, you can see 2 buttons at the top. You can do a new plot if you got a whole bunch of noise and you'd rather start those things over again. Or new file, we'll click on a new file. Just below your cursor, it says default KS for Kansas in the middle of the United States. And then it has a date, 25 for the year, 04 for the month, and 14. And then you started in the UTC hour of 16. And then it turns out this was the second file that was started in the 16th hour. So there's a letter B after the end. If you would press new file, it would simply start a file called C.txt, and just keep walking along. It'll do that about 25 times, then you run out of numbers. So,
What happens then, Ted, when you get to Z?
I think I give you an error. It says I can't make a unique file name. What are you doing?
Yeah, stop it already.
Yeah, right. Leave me alone. There's a way on the left that you can adjust. You can document what your antenna is pointing at with azimuth and elevation. Later on in calculations, we need to know that. You could do it in right ascension declination if you want to, or galactic coordinates. I don't care. But this one is azimuth and elevation above the horizon. There are knobs all over the place. Eventually, we start studying. This one is looking at 1420.405 megahertz. It says in the top right there, one of those big numbers. And then the next step in progression is, well, it would be better analysis if I could compare it to no hydrogen. I want a reference sample. Give me a sample of this thing working right now at this temperature and everything else, but without any hydrogen. So how about looking at 1423 megahertz is just a guess. And then now we can get the number. These graphs will bounce up and down, alternating between 1420 and 1423, back and forth and back and forth. So the steps never end.
If anybody's interested, I could show you that in action. Would anybody like to see that?
Yeah.
Okay, so I share my screen.
This is all described in that demo PDF I speak of.
Yeah. So, so this is a live data collection at the moment coming from the Ptarmigan array. And what Ted is talking about is you can see it both in the hour-long plot and the day-long plot at the bottom, where you can see the zigzagging line up and down. I have quite long file names, which are quite descriptive, so you can hardly see it. But if you look above freak center, for frequency center of 1,420, just above it, sort of just about visible, is 1417, which is actually my the frequency I'm using. Now I've gone down rather than up because there was some reason to think that I was getting a slightly better correction at that because of some RFI that was there, but whether that's true or not, I don't know.
And now once you have samples that have hydrogen and samples that don't have hydrogen, let's compare them. In fact, let's compare them live. So you clicked on ref div up in the top right, and your graph looks different. We are dividing frequency by frequency the antenna power from the last sample divided by the reference sample's power for that frequency by frequency all along. And there's kind of a bump a little bit to the left of the graph in the top left, showing, yeah, there seems to be hydrogen at the moment. Great.
The other thing is, anybody who's quite might have noticed that my EZ col integ quantity number, there just below, there's new file, then it says to file, idle, exit, and then down just below that, the first grey box is EZ col integ quantity. So that's the integration quantity for EZ col on this particular computer for me, and that, it doesn't say 31,000 as Ted's using it, says 280,000. So I felt that having a million samples was a bit too much to try and process, so I've actually gone down to samples that integrate over 4 minutes or so. The argument being that the size of
224 seconds, yeah.
Yeah. So and the argument there is that on the basis of the size of my aerials, that it doesn't really matter too much to get anything much shorter than that. But it does mean that it takes a long time before this graph updates. So if you're in the process of trying to test things, you might want to go for a shorter integration quantity. It's worth noting that in easy radio astronomy, you can't set that as a particular time period. That all depends on the speed of your computer and how fast your RAM is and your hard disk and all that sort of thing. So you have to do a bit of iterative testing until you find one that gives you the sort of length of integration that you want. If you don't mind, I've got one little thing I do want to show people, if that's okay. A couple of things. So where are we?
More icons on your desktop.
Sorry, I know. Yeah, I know I'm on the desktop. Yeah, I'm just trying to find something. I put it here, and it was all logical. I was sorting it all out, and I've forgotten where I put it now. Here it is. Too much stuff. Right. So you can see the PowerPoints come up.
Yep.
It's only a couple of slides. Don't worry. So it's just some pictures of my setup as it stands at the moment. And I'm going to point out that there's a third. So these are my hydrogen line telescopes. So the one on the left-hand side is the ptarmigan array. That's sort of 86 centimetre by 86 centimetre 4x4 dipole. Then the one in the middle is the 1.5 metre dish. That's the solar cooker dish. And you'll notice that next door to the washing line, there's a new one that's appeared. So I've spent the last couple of days making that another one of my simple wooden drift mounts. And that's one of Alex Pettit's 13 element patch Aggies, which I'm trying to set up. So just so there you are. There's the patch Aggie. At the moment, it's covered by silver foil at the bottom because I haven't actually connected it up to anything, and I just didn't want to get any water ingress.
So I see an antenna just to the right. It's got a lot of wires up in the air. What frequency is that one?
Oh yeah, that one. Yeah, that's Radio Joe.
Good for you.
Or more accurately, it's my wife's washing line. Right, where we go? Okay, right. So I wanted to point out here. So this is my solar cooker scope. So I've had a bit of issue with this, particularly in terms of drift. And when Ted and I met recently, I got to say, first of all, Ted, I want to say that it was very nice of Tony earlier on Andrew earlier on to give me credit for trying to help him out with his scope there. But it was almost entirely you that gave him the advice the other day. And then when you and I met up, one of the bits of advice you were giving me was how to use corrections in easy radio astronomy to compensate for the telescope pointing in the wrong direction, or at least the measurement being wrong. But looking back at my data for this particular telescope, I've concluded I'm getting some drift occurring, and I think it might be because the metal struts that I use to to hold up the waveguide are only sort of simple flat pieces of steel. They're something from roofing struts or something from a local hardware shop. So I think it's just moving around depending on the angle of the dish. So you can see there that I've put these reinforcing poles in. In the UK, it's very expensive to go to a hardware shop and say that you want to buy a wooden pole or a piece of wood. That sounds ridiculous, but anything that's sort of basic like that is incredibly expensive. The cheaper way to buy anything is to go and buy something that was made for some purpose. So these are actual 3 broom broom handles. They've been spray painted, which makes them look like they're sort of metallic, but they're not. So that's and they will be cut down to make them a little bit neater, obviously with some cable ties to try and attach them to the existing struts, try and give some strength. So I'm hoping that will make things a bit more stable. The other thing you can notice is that there is what is in fact a wooden stick coming up through the middle, and I'll explain that in a second. The best way to explain that is if I go onto my website. I put a couple of pictures on there. Right. So I was saying that things looked like the measurement was off in different directions. So one of the problems I've been having is that in terms of measuring inclination, if you take this central pole out of the equation, then what I was left with was putting a digital inclinometer on the inside of these petals where it bends over. And I thought maybe that would measure it with enough accuracy, but I think it wasn't very accurate at all. So I've put this sort of central stick in. I think it was something I saw on Ted's telescope, so I thought that sounded a good idea, and maybe I can copy that. The question was, how do I actually get it in the center of the antenna? So you can have a bit of a laugh. This is my exercise with a load of cable ties in order to try and find the central location of the antenna for my stick. I have no idea whether that's a good idea or not, whether it will stop a certain amount of signal getting into the antenna. But that's to give me a stick that points out the back, so I can now put the inclinometer on it and get a reasonably accurate elevation. And I've already found that the elevation that is recorded on that is actually quite substantially different from the elevation that was being recorded by the previous method. So hopefully I can now get some data that looks somewhat sensible. That's me. Any comments are gratefully received, including negative ones.
Very practical.
A quick way of testing if the material you're using is RF absorbent is just to put it in the microwave oven and give it 30 seconds. See if it gets warm. If your cable ties get warm, they've probably got a bit of carbon loading or something in them. Don't use them for that job.
I will make a note. Put cable ties in microwave oven.
Only when the wife is out. Yeah.
She's at a course tomorrow night, so I can do that.
It's just a 30-second test. If it gets warm, then it's absorbing. Not good.
I'm writing this down for 30 seconds to see if it gets warm.
I don't know, Heather, you may have other ideas on that one, but
if you're playing the game with the health and safety elves, then you probably want to put a glass of water or something.
Say, yeah, a small amount of water in a glass to the side would be useful.
Well, what does that do?
That absorbs the microwaves in case you're just heating up thin air and then you're going to crack something.
Yeah.
Oh, what? If you turn a microwave on without anything in it, you can crack something, can you?
They like to have a load.
Oh, no, I didn't know that. I didn't know that. So, Andrew, are you going to bring your aerial there along to Yukara?
You're muted.
We can't hear you.
Yeah, I can do that. I haven't bought my UCARA tickets yet. I need to get organised on that front.
So I put you off buying any. So for anyone who doesn't know, so UCARA is the European conference on amateur radio astronomy, isn't it, being held at Harwell Conference this year. So is there anybody else? How about you, Paul, Heather? Would you like to say anything at all or comment on anything that you're doing?
Not really. I think we haven't really done very much. We're a little bit behind John ACD on getting all this kit together. But
that's the receive chain as we stand. Interestingly, the filter box there is available on eBay and AliExpress.
Oh, is that one of these little sort of £10 ones, are they?
Yeah, a little bit more, but yes, it sweeps 1325 to about 1500 megs as a bandpass. So it's not quite so sitting neatly across 1420 as you would like, but it certainly gets rid of strong stuff either side. I haven't tested this out yet, and the next stage is it claims 63 dBs of gain. Well, that's Chinese decibels, so we'll see how that works.
Well, one comment you made some time ago to me, Ted, was we were talking about cavity filters, and you commented that trying to get large amounts of attenuation out of band these days possibly was less useful than it used to be because you could use software to achieve a similar effect. So I'm not trying to put you on the spot, but when John describes his Chinese filter there that's significantly cheaper than the New Elec Sawbird, does that give a significant disadvantage, do you reckon, given that we can use things like Easy Radio Astronomy or other pieces of software to achieve a software filtering solution?
Hardware filters have their use, but my gosh, our signals are so weak. That's what you've been experiencing. Perfect filters would be even better in reality, but those are very expensive. In the meantime, we play with the software.
Yeah, easier to engineer in software with squarer edges.
Unless you've got an adjacent signal that's so strong that it overloads the SDR.
Well, that was really the game of that rather crude filter. It was just as a basic bandpass from 1350 to 1500 with the radio astronomy in the middle. But I don't know how much loss I'm actually going to incur and whether I can experiment. I can take it in and out of circuit, and that's what this is about after all. Experiment and see what works.
Yeah, interesting to see whether you can map the Milky Way with that.
Well, the idea was to put this at the focus of a 3.7 meter dish.
Oh.
So not just that. I've got the dish mount, the sort of the central focal point mount in the workshop at the moment. I'm trying to work on, and then wait for the wife to go out for the afternoon while I move the dish into position.
Does she know about it?
Vaguely aware.
I was actually offered last week or the week before. I was offered a free 3 meter dish.
Yeah, I dropped an email to the group.
Obviously, you did it, was it? Yeah.
That was from me. It was posted on the UK microwave groups, groups.io.
Yeah, well,
so I shamelessly copied it and dropped it into email to us.
Well, I contacted him and he offered it to me, and I was going to go up and pick it up, and then I worked out how big it was going to be in the garden, and I thought my marriage of 26 years was probably more important, so I didn't go. So it's still there if anybody wants a free 3 meter dish. You do have to go up to Huddersfield, and thank you very much for posting it, John.
That's all right. I saw that and I thought of you guys.
If anybody does want it and can't move it, we could help out. we've got a trailer, as has John, so we can.
Yeah.
It's worth saying he's already got it dismantled.
It should go in the back of an estate car, I think.
The petals are 2 meters long.
Oh,
One for you, Andrew. I did drive home one day with a 6-foot dish with the roof down on a Triumph Spitfire. I was holding the right-hand side of the dish, and my passenger was holding the left-hand side of the dish. He was operating the gears, I was doing the steering. We weren't going very far, but it was an interesting journey all the same. But there's no way you can put a 6-foot dish in many cars anyway. So I thought the easiest way to do this is 2 of us in a Triumph with the roof down.
Dear.
We managed a 12-foot dish in 2 pieces down from Scotland, so there's all sorts of possibilities.
So Paul and Heather, have you got anything else that you would like to mention or discuss?
I do have a question. What do we think about the difference between the dish and a Yagi? I know somebody early on gave us some information about what the equivalents are. Because we have lots of dishes and lots of Yagis, so where would be the right place to start from, you think?
I have used both. I think somehow dishes collect a little bit more power at the 1420 megahertz frequency we care about here. Other frequencies lower, I think Yagis win.
Yeah, the crossover is somewhere around gigahertz, I think. One disadvantage of Yagis is that their side lobes can pick up ground radiation, so you've got a much higher temperature there. The dishes,
you get a massive amount of ground noise off the back.
Yeah, the dishes, if you slightly under illuminate, will give you much less ground noise.
Many options.
Yeah, that's very good.
I'm just looking up my friend Chat GPT to see what
You're brave.
to see what he says or she says. So what we got? It says serve different strengths and trade-offs depending what you want to do. A parabolic dish will give you high gain, very high directivity, and ideal for faint sources. A Yagi will give you moderate gain, by which it means 10 to 17 decibels, as opposed to 35 to 40 on a very large dish. A wider beam width and good for general sky surveys or broader surface sources. And then it goes on to say about weight constraints. So.
Yeah, I guess once you're getting above a metre and a half, then you're really better staying with the dish than the Yagi.
Yeah.
Once you're up to that sort of size.
With a dish, a lot's going to depend on the feed, as to whether you're spilling over the edges or you're under illuminating in terms of ground noise. Gain isn't everything, it's G upon T.
Yeah.
Which is important.
Because this in itself isn't that brilliant in that respect. Because that dipole's going to be picking up a lot of noise from behind the dish.
Yeah.
So that in itself might need to be inside a cantenna or some other focusing device.
Yeah.
Again, part of the everyday being a school day. It's a learning curve.
So, talking that then, John, is it?
Claim that thing just out in space in your backyard would pick up hydrogen. So it's just improvement upon improvement.
Yeah.
Yeah.
Again, that antenna was a preformed one from AliExpress. I got a bit click happy. The postman starts bringing all sorts of nice things.
Yes, just one observation about filtering. Down at 1.3 gigahertz. I had a system which had a Yankee on it, about a 37 element Yankee. And we were picking up quite a bit of noise in one direction. I put a nice tight low loss filter in before everything, and we got a 14 dB improvement in signal to noise ratio. So
Wow.
external out of band signals can give you quite a lot of problems.
Yeah, a strong out of band signal nearby will desense the front end of one of those receivers, those cheaper RTL receivers. It'll flatten it. Yeah. So if you can have some fore-end filtering, then that would save the front end of your cheaper SDR from being clobbered.
Or your preamp even.
Or preamps, yeah. I mean, that's a 63 claims, a 63 dB gain preamp.
Yeah. That can easily overload your SDR if you're not
That would easily overload. That might be too much. I've got some 20 dB variants as well. 63 might be too hot.
Yeah.
If the local noise is too high. Luckily, where we are in the middle of nowhere, there is no noise really, unless it's self-generated. But all the Wi-Fi links locally are at 60 gigahertz. It's only when it drops into the houses around the farm here that we drop down to 2.4 gigs. There's not a lot of radio noise locally. In fact, it's the LED lighting in one of our own buildings half a mile away that makes more noise than most other things around here. But you'd be surprised what does generate noise. LED lights are on my hit list at the moment.
Which gun are you using?
There's one here.
So, talking of people's things like that, John, that you're doing, or anybody else, I've ordered a table for Yakara in September. So if there's anybody that wants to, doesn't want a table of their own, but would like to just put on something to display, then you're welcome to come and share my table with me.
We can bring some toys to the party. I've booked my ticket the moment it was all announced, so we'll be there.
Yeah, but I'm saying by all means come and share my table if anybody wants to, and you don't want anything separate yourself. I mean, obviously, if you want your own table, go ahead and do it, but I'm trying to put you up.
I'm afraid we can't make it because we've got something else on, which is very annoying.
Well, likewise, I've ordered a poster board, so if you want to get a poster done on anything and put it up behind the table, you're very welcome as well. And I think there might be a little bit of funding for posters. I'm not sure. Anyway, so Jeff, is there anything else that you'd like to talk about?
I'm supposed to bring some information regarding SDR Sharp. I have some slides to share. I can show you what I'm doing. And I do have some questions that maybe I can get some help with.
Did you say you had some slides to share, did you say?
If that's all right.
Yeah, sure. You're sounding quite quiet. I'm wondering whether that's due to the rest of us being with our microphones turned on. It might be worth us muting our microphones.
All right. Well, this is kind of like my setup here. So I got like the 3-meter dish, and I made a looked up online for a beam of form with a smart choke, with cutting up, and I use the SDR Smart T and the solver. Primarily, though, I have to figure out I'm just doing drift scans, so I use like radio eyes the last year, which helps me figure out where I'm pointing and get locations, things like that. And with SDR, it's an old program, and I guess it was just the first one I found. I kind of regret going with it at the end, but it worked. Once you have everything set up, it worked pretty well. I've done something on here. If someone really wanted to use it for the first time, you need to get the if average plugin. So that there's your state from the SDR, and you get your signals. That's a bunch of junk in it, and you point it like up to the north folder somewhere and you acquire a background, you get a nice flat curve, hopefully. And the settings are, there's a couple of web pages I have at the end of this that I stole the settings from. The gain is kind of obvious. The stronger you want, the level kind of moves the plot up and down. And with the averaging, it's weird. I don't know how programmers set it up, but 90 million ends up being about 8 minutes for a scan, for calculations that end up getting the signal. And so what I basically do is just, I have a remote access, and there's the current, no, not sure. I can remote into it and set it up and walk away. So it's set up like here to do a scan every 8 minutes to correspond to it, and then I can just go backwards and figure out what time the object I wanted was drifting through the beam and look through the folder. Nice program I found was Chronolux. One of the ladies told me about. It takes screenshots, and I can set it up with screenshots for the same amount of time. Like I got a time capture about 8 minutes also. So it's a nice way to look using radio eyes. Here, it's dictating that there's this little circle up is where the beam is pointing, and there's my signal to the right, so I can kind of look at it and make sure everything's okay. So it works pretty good, and the Chronolapse, it saves the screenshots. I can go back, look, compare the scan to the screenshot, because I don't want to be live. Another thing I ended up doing is that I did make a video that you can do with all the screenshots. Kind of works out pretty nicely in terms of looking at signal over like a 24-hour period. And I need to use this Microsoft Teams. I might help myself out. I'm going to try to change how I change the screen. I'm going to keep on going. But if you want to see that, I can show that later, I guess. And,
you would have to unshare and then share another window, is what you're fighting.
Okay, I'll worry about it. If anybody really wants to see the video, I've got some people like music in the background. And I was actually, the sun happened to go through the beam, so you can see all the frequencies kind of go up and go back down, and that's kind of how I double check the beam width really, really well. But from the scan, I could dump the text file, and I could graph the text file, and then I just look for the peak. And I'm doing a galactic rotation curve primarily. So I look for the most redshifted one for the tangent point. And I got pretty decent data last year when I tried it. I decided to go, and I got a Python script. One of the things I was worried about is like the bottom graph, where the peak is not necessarily sticking right out. The top to the left is pretty easy to see. Four major clouds, and you could get the peak frequency for each one and get the velocity. I'd look at the one that's the most redshifted to the left, but like the one at the bottom right is a lot more complicated. And I'm working with like a Gaussian type program and messing around with some of the variables to try to match different Gaussian shapes to determine the different clouds that might be overlapping. So my first question would be, what are people doing for looking at the lower scan? And I want to separate the different clouds out. How do you do it? Anybody?
So why would you care about a particular cloud? You're studying the red-blue shift, I understand.
It's trying to get the rotational curve. So I'd like the most redshifted frequency. that's along the line of sight to calculate the velocity.
What I've seen is that you have the overall curve in purple there on the bottom right, and you come, let's see, what is it, from the higher frequency, and you come down, or is it the lowest frequency? Anyway, you pick one at a certain value above the baseline and say, bingo, I found it. And so it's only a one frequency output for your calculation. Why do we care about all the different clouds that make up this complex curve?
All the different things between us and that spot in the sky that I was pointing at.
So if you have three different clouds down there on the bottom, I see that make up the complex curve, but we only care about, I forget what it is, the right one, most one, or the leftmost one, highest or lowest frequency.
Yeah, the most left one.
Okay, and so why can't we just use the complex curve to come up with that frequency?
Well, it's just, I guess I could look at it visually, that spot there, and say, okay, there's probably a peak here, and there's probably a peak here, and a peak here, obviously, and then another peak back over here. I just want to get more than just sort of an eyeball. If there was a mathematical way of figuring out
I've seen other folks do this as well, and it always seems to be a hand process of coming up with those parameters. I agree it's a difficult problem. And then I just kind of wonder why it would be needed. But I agree it's complicated.
Somewhere where you can pass that software, which is only on Linux, would do that. And it's a little bit more complicated for what I'm doing. So either way, we'll see what I decide. Next thing I do want to do is mapping. I've downloaded the Easy RA onto a Raspberry Pi, and I ran it only through my SDR so far. And I'm putting an antenna together downstairs. This dish is going to be taken apart in about another week to motorize it. I've got some students doing some data at a high school, and I'm kind of like, they're just looking at visually the post-redshift frequency, and I'm trying to do a little bit more of a more complicated analysis, really get them that lowest frequency. So there's what my graph looked like. One from last year on the top left, kind of ugly. It had a bunch of points, I think like around 30 degrees, trying to get a better shape out of it, but they all always gave the same, pretty much the same value. And now when I'm playing around with this Python script, I'm getting the lower right kind of graph. And we're not quite done. I'm out to 70 and trying to probably set up, going out to the location on Wednesday night, rotating the dish so that it can pick up 80 degrees longitude and see what happens. So SDR Sharp works pretty well, especially if you have like an old computer. This is kind of like a couple of the articles that I found when I first started this. The dish was at our Astronomical Society since early 2000. Different groups have tried to do this experiment, and they've all failed. I'd say mostly because the technology was too expensive, and one of these SDRs was LNA came out. I go in and I just automatically, the first time I hit the first light, I get a signal. And it was rather exciting, and felt kind of bad because a lot of the other people that showed me all the money they spent on different things, like spectrometers. I think it was like $8,000 or $9,000. But anyway, it was easy. There's a couple of different websites you have to be careful with. Strangely, the newest version of SDR Sharp does not work with my old system. I'm using an old computer, a Lenovo laptop that the school that I worked at, I retired 2 years ago, was going to throw away. So I think maybe that had something to do with it. I don't know. lot more to do with the if average plugin. It is an old plugin, and unfortunately, the gentleman that developed it has passed away. He's a young guy too. I forget when it was he passed away from. So when you look up things, there's a lot of dead links to the old if average. You can't find it. Yeah, there's Daniel Kaminsky. You know.
Sorry. Are you
I don't
saying?
think anybody's really,
Forgive me, Jeff. Are you saying you can't find the
updated.
latest?
That may be why the older versions of SDR Sharp work better than the new ones, or I couldn't figure out what the new one, and the old one worked. That's fine. A couple of different people. Yeah, go ahead.
Sorry, Jeff. Are you saying that you have not been able to find the latest version of IF average?
I don't think that. No, I don't think this is not a.
I'll send it to you.
Still works.
I'll send it to you. I've got it.
Okay. Someone else redid it or something, or is it this?
So you have a name down there with, I'm sorry to say, a death date. He has updated his software since that time, so we have a confusion of names. I think our fellow is in Prague or Czechoslovakia. We think I think he's a physics professor, and he wanted this IF average essentially for his labs for the students. But he sure doesn't want to support it. I don't blame the guy. And so he has posted one update at least that we want to get to you. And indeed, it is not compatible with the latest SDR Sharp. And that's the problem you have found you out yourself. You've gone down the same path as many others before you. We agree. And I would love to. I've been trying to update this software, the IF average, for the latest SDR Sharp, and it's not easy, having to do with Microsoft software levels and all kinds of stuff. There is much more hope here. This is good. You're going down the right path. And of course, I suppose I'm forced to say that the IF average data can be converted into Ezra to do more math on it, if that's helpful to you. But you're doing all the exciting, fun things. Well done.
There's a little link that someone I used helped set it up, and then I thought, with recommendation, I thought it was a good starter program for me. So I've never done anything like it before. Once I got through the bugs, things like that, but there's a lot of limitations after seeing that Ezra. I'm going to be switching over. I'm going to give the computer. There's another computer that I got from school that's being used for Radio Jove at our location. Having Wi-Fi issues, and I said he can have the one I've been using. I'm going to really try to do on a Raspberry Pi. It just looks like it's a lot nicer. There's more support. I don't know. I guess a lot of people are using this SDR Sharp. You're updating it. It just seems that you have to do it other things. You use it just to get the data, and then you can't really do anything else. But I'm seeing out of what your program is, it's a lot. It has a lot more detail.
SDR Sharp is a convenient software because it talks to so many radios. It supports so many things. That's why I keep talking about these SOAPy drivers. And SDR Sharp is great for that. It's a little complex. It's got a lot of knobs and buttons. But if you're led through that maze, it works great for collecting if you use the old version of SDR Sharp with the right level of IF average. So that's the maze. Others can help you through that maze. We want to help. But there's also ways to take that data now and analyze it with all sorts of other things, including Ezra. Lots more fun to come.
Okay. And that's all I got for now. I guess next time I'll be asking questions about Ezra. That's what I was doing while I was missing the time with everybody else. Is putting together my box for my LNA and my noise source. And I'm going to put a little antenna out front. I've already got the okay for my ham radios up in the attic. I that. But I'm going to have a little small little 3-foot antenna just out in the driveway, pointing to the east, because that's the only open area that I have. And see what I can do. I've only done what Andrew did, having the first string and seeing the shape of the SDR, like, okay, I'm getting something. It runs for an hour. Okay, I got goes up and down, but I'm not measuring. So I'm confident that it's going to work. And I'm sure I'll have questions next month.
Yeah, keep going. You'll
Andrew
definitely
was
get
saying
there.
one fellow couldn't join us here today, and that would be Alex. He's a great proponent of the SDR Sharp process because he is studying to improve antennas, and you get immediate feedback from SDR Sharp that way, which is just great. And he's got a way to compensate for some of the temperature variations we get during the day, for example. Ezra has a different method using those reference samples. I like all this experimentation. Let's all find different ways and improve the overall collection. Excellent. Jeff, that was fun.
Well, that's wonderful. Thank you all very much indeed. Sorry, John, did I ask you whether there's anything that you'd wanted to say?
Nothing more to add, really, on this one. I've got a concrete pad in the corner of the garden, a dish at the other end of the garden, and a nervous wife in between.
And Andrew, is there anything you wanted to add further to what you said before?
No, nothing from me.
No. So I think it for me to say thank you all very much indeed for taking part. It's been wonderful. And would you like to set another date for another one?
Oh, yes.
All right, that's good. I was asked by Paul Hearn, is this something that's a one-off or is it continuing? And I think it looks so far that it is continuing. So as long as people find it useful. I mean, a month from here would be the 12th of May, but I'm not particularly wedded to that date. But it depends how you guys feel.
Any time that week?
Ted, Heather, Andrew, Jeff, all okay? Yeah, great then. So,
What time? So I don't mess up.
well, should we go for the same time, which is 7 p.m. British summer time, which is UTC +1?